Hi everyone. It is Friday morning here in the classroom. I'm going to continue on talking about the polymers, just closing up here on plastics. I had a few things to add on to the example I talked about regarding the composite tanks. And just like I've done the past 5 or 6 years, I sort of changed today's class a little bit based on the feedback. There was a lot of class participation yesterday, which I appreciated, and it's sort of directed at a little bit of a, I guess, a more focused and perhaps interesting direction for today. So before we go, so the agenda, recap, the whole the forming, and then we're going to go, is this today? Yeah. Okay, there's two summary here. Yeah. All right. So before we get into the details, there's one thought I want to offer to the class. Professor Eager, Dr. Holman, and myself are teaching this term and trying to, really talk about practical engineering. So to some extent, we're intending for this to not be just a scientific or even engineering type of, cooked up recipes. So I wanted to share a little bit why I don't have the tie and everything today is I am running a small company. We are making a technology innovation, and we have to bring it to the market. At this point, we are also becoming a service organization. And it's a tall task. It's very, very broad. And to a comment, Greg, that you made earlier, that mechanical engineers tend to have PhD theses that are more applied. What I'll say also is mechanical engineers tend, in greater proportion, to become managers of projects or business managers. And on that, it's all about really what your core skills are, and to some extent what interests you as a student leads to a path for your career that suits you. And as far as the class, we embrace diversity. And at the same time, I realized that from the questioning generally in this class, that it's more about the applications than the academic side or the science side of the class. I mentioned in the last lecture that I'm making a commitment to give you guys enough depth into the topics that I'm covering so you are able to build your own foundation. And it's by no means it's supposed to be a complete foundation. We are more trying to express to you guys that are young in your career all the options that are there. When Professor Eager teaches about what is engineering, it's very popular and we can understand why. This specific topic for this module about processing and application of material already sounds more academic. So maybe somebody could suggest a new title when you're done, when you do your one-page summary. That'd be interesting. I'd like to hear that feedback. So now, without digressing more, we will go to the topic for today, which is to wrap up things I've said about the polymers. And I talked about degradation. We had this tether support yesterday, and I drew it on the board, and we talked about that it had some fatigue loads on it, and it broke. And in this case, it's black, so it had some particle to protect from the UV light on it, and therefore it wasn't an effect of the environment initiating that failure. And that was a question that Brian asked that was right to the point. He's also an expert in some of these topics. So I mentioned about this example very briefly 2 lectures ago, the degradation of tubes. Good morning. Thank you for coming. I want to go into more depth now, so we hopefully can all remember something, because I tend to be sometimes a little scattered, right? I cover a lot of ground very quickly sometimes, and that's why the questioning is very good, and also kind of doing the recap hopefully helps. So let's think about it this way. So we make a plastic, and I'm going to make it as a box, make it simple. And we're going to call this plastic polyethylene. Now, what we do with these tubes, and I have one of them right here, it's deformable. So that's why it's not like a rope or anything like that, but it really is deformable. It's hard to kink too. So in a home, because it's got a thick wall, and we discussed that last class, so it's less susceptible, this one, to the lateral buckling or the shell buckling phenomena. So let's see. You good? Sorry. So this plastic was cross-link, and and we call it PEX, P-E-X. If you're more interested in how that happens, Wikipedia or Google, very easy. For today, just to stay a little focused, assume that makes the plastic better. It cross-linked between the different polyethylenes, so you don't have as much of that creep behavior that we've talked about that happens with those polymers. That was, I think, 2 lectures ago. I talked about spaghettis, things like that. So it's good. It means that even though it's very flexible, it's not going to burst under pressure for an extended period of time. You put this in your house for 50 years, and you don't want to leak, and so you don't want it to burst. So it has to be good, even though it's super soft and flexible for installation purposes. Okay, so one nail down. Now, if you're going to use this material in the presence of oxygen, and oxygen does exist in potable water. So what happens? Oxidation. Yeah, you can oxidize the polymer, especially if the water is hot. You're thermally activating that process. So what do? You put the antioxidant. And by the way, I say you can ask me any question. If you ask me exactly what the antioxidant is, I'll tell you today. I don't know. I can go and find out. One of my friends is really an expert, a word expert on it. Something like that. Okay. So the antioxidant exists in food. You go and buy some cheap wine that was in bottles in a very fancy way. And I won't say if it's French wine or California wine, but some wine. And it'll be good for a while. You open the bottle, everything's fine, and then all of a sudden it turns vinegar. Okay? So what happens when it turns vinegar is all of a sudden you depleted your antioxidant. And the life is not good anymore. The wine's not tasty. And here with this PEX tubing, instead of being white, it becomes yellow, and it starts causing all sorts of problems. So maybe having explained a little bit more about the material, just a little bit about the process of the oxidation. So the part that I did not explain is what do the antioxidants do? I didn't explain, right? But so they're very, very small molecules that are into that plastic there. And they just sit there. And they wait for one chain of polyethylene to get ruptured. And then they go and put a Band-Aid on it. That's a simple way to think of this. And therefore, it can't really prevent the rupture, just like a Band-Aid cannot prevent you from getting hurt. But hopefully now that gets your mind thinking about what's going on in there. So if you have a very rapid degradation on the surface, it could be that the little antioxidants that are deeper in the material don't get to the surface. So let's do that very clearly here. So we have a pipe. Turns out we put this water in that's just terrible. Okay, let's just say that we just did a bleach of the potable water system, and there's just all sorts of stuff in here. A lot of activity, a lot of reaction. So it is possible that even though you have still a concentration of antioxidant here, you may be at 0 here. So you damage the interior surface of the pipe permanently. Can that happen? Let's not talk about that. But at least you understand a few more things here on the process. Okay, so I think we're good to talk now about that special tubing. That's the one where you can deform it, but when you let it go, it doesn't become straight, so it's not annoying to put into between the studs in the house. You put it into shape, it stays there. This is what everybody likes. So the aluminum layer, aluminum's normally pretty good in terms of corrosion resistance in potable water. I mean, we could have a bunch of aluminum pipe. You know, you can boil water. The aluminum, it may cause Alzheimer, things like that. But as far as containing the water and not corroding, you know, it's fine. Okay, so what happens here? Like I said last class, they used this tubing, and they didn't think about it twice in terms of adding more of this stuff because they were going to use potable water as opposed to a closed-loop heating system. If you have a closed-loop heating system, like some of you probably live in old houses that can have all sorts of very old radiators, things like that, and maybe one day you wonder why is that, you know, leaking after 80 years, and the main reason is you paint on the outside so it looks good, and on the inside, if it's a good closed-loop system, if it doesn't have leak, then there's no more oxygen coming in, so the corrosion stops. Am I making sense? Any questions so far for today? Yeah? Is it interesting? Okay. I'd like just one question, please, if you can, today. What do we do here? We explain that maybe the inner layer of that super cool pipe that every plumber wants is going to turn vinegar during service. That's more or less what we said, because we said it's a good material, it's got antioxidant, but there's enough oxygen that you deplete the entire surface, and now it's essentially when you have a rupture, you cannot put a Band-Aid on it, so it's bloody in there, and bloody in the case of this polyethylene means the environment becomes acidic. In an acidic environment, pH below approximately 3, the aluminum will corrode very quickly. So if you think as a designer, I don't really mind the internal layers just so the potable water doesn't touch the aluminum, and therefore I can't be blamed for causing Alzheimer type of thing. Therefore, let's go, let's sell this. Then, you know, years later, start getting these bursts here on these pipes in homes, people are unhappy, and then what do? You blame something, right? You try to find out what's going on. But as part of this failure analysis here, I think you can acknowledge that we had to piece together different pieces of the polymer engineering. We did need to kind of understand that this could oxidize, that there's an antioxidant package, and that the oxygen had to matter to it, and then that it was going to change the pH, it caused the corrosion of the aluminum, and therefore that's the reason for the burst. It is nothing else. You know, it's not like other theories. This was a big problem. It started, I think, maybe 15 years ago, and it's been resolved after a while, of course. So there is some literature on it, and I don't mean here in class at all to pretend like I know everything about it. But as far as a class example, we apply a bunch of different concepts that you and I talked about, and I think we arrived to something that makes sense. You know, and then the way to fix this now is just put more of it. Put more of the antioxidant. Yes?
So basically, plumbers really liked the stuff and started using it off-label, like for a non-prescribed use. And then the manufacturer maybe didn't even know that it had this issue. Is that?
Yeah, it's a very good question. So the comment from Greg was, well, so it sounds like what happened is the builders wanted to use this even if it wasn't labeled for this use. And I mean, honestly, I don't necessarily remember the answer, but of course, now you're bringing another important topic of engineering and business, which is building and clarifying the customer expectation, and at the same time, kind of the specification and the promise to the customer. And what I'll say to that is this tubing was governed under an ASTM specification. And I don't know, you may be taught in class that ASTM is really good because it tells you how to run a test, for example, you know, pull on a sample or run an antioxidant test. But in terms of performance specification, it's not because it's ASTM that it will meet, and that it's not either that it will be very clear on what to use it for. It should be. And unfortunately, to the question from Greg is, yeah, I mean, the plumber is not going to read the ASTM. He's going to go by what the person perhaps at the plumbing store is going to tell him to do, but at the same time, that person's going to want to make him happy. So if he wants this pipe, and the person doesn't know anything about it, who knows what's going to happen. But these are all real issues. So when you make a product into the market, there is a long series of steps involved in terms of being clear about what it was designed and manufactured for and what it was not manufactured for. And you know, sometimes you do have the unexpected, and that's again part of the service history. So, I mean, yeah, I think we covered it, right? That's an example, probably more understandable than when I flashed it 2 lectures ago. This one on stress corrosion, maybe we covered it enough because we talked about the ore inside the pipe acting a little bit like a lubricant to help start the crack initiation. That's a little bit intuitive. So this one is a CPVC that we have here, which is CPVC is chlorinated PVC, and chlorination, a little bit like the cross-linking, it helps you with creep resistant at temperature and things like that. So commercially, you can have PVC, and that's if you go to the plumbing store or the hardware store and you look for drainage pipes that are white, the little elbow and pieces like that, generally they are PVC because it's used at ambient temperature. You know, water that comes from the shower, yeah, it's a little hot, but it's not pressurized, and therefore the PVC will do the work. If you're thinking about using the similar type material, but not high temperature to carry your hot water, for example, the shower, now you're into this level. of the CPVC because you need a little bit more of a creep resistance. Well, nothing's perfect, so by adding this chlorination, things like that, it does make you more susceptible to the oil and things like that in the system. And it's been a big challenge in the fire sprinkler industry. Any questions on that one? Okay. The composite pipes. So over there, I mentioned about that they were both used. The steel tank were used and the composite tanks were used. And I said very, very briefly that sometime with the composite, you can have something coming out of the factory refinery that could affect the performance. And then I worked out of the class, and even if there weren't any questions, I started thinking, was that a good example? Well, it's better than nothing. That's what I always try it here. So I thought about it a little bit more, and I happen to know that for making those pipes, when it became standard to add alcohol into the gasoline, that they had to change the formula. They had to spend more money in that resin because now, hey, it really had a solvent that was different. The alcohol is a form of solvent. So maybe with those three examples, and we could really go on and swing the music, for example, with nylon, which is used a lot still, well, less than it used to be because of that problem. So nylon as a component in a car, for example, is very susceptible to moisture. So it's going to have different mechanical property. If it's in a dry environment and in a wet environment, it's affecting what we call the glass transition temperature. And therefore, you're designing for something, but it varies a lot with temperature. So what did they do? Said, nylon, it was a great invention, but why don't we have a nylon that is less susceptible to moisture content? And I guess to be clear on that, we're talking about maybe 2-8%, and don't quote me on numbers here. I'm really trying to provide some examples. So let's say it's 2-8% water that nylon can take, and then you have another polymer that will only take 0.5 or 0.2%, just as an example. Well, the properties of the one that absorbs less water are going to be less dependent on the environment. So I guess that's another example. Essentially say when you think of a polymer, you don't want to just think, oh, well, it's brittle at low temperature, right? I think people know you have a food container and it's late January here in Boston and you drop it on your way home, maybe the corner is going to break, and it wouldn't break if it was the summer. So that's something to keep in mind, and that's something that really just has to do with temperature to some extent. But we've really been clear, hopefully, and I think you guys are going to keep in mind that when you pressurize a plastic, it will expand over time. It really has creep. There's no avoiding it. And then in terms of this, what I call degradation, hey, let's be positive. Let's call it, polymer environmental interaction. It's still the same. It's a change in the behavior and the performance that is due to contact with the environment. Are we ready to talk about steel again? We're going to switch the music. So, I brought a rebar. So that's a piece that was given to me by another engineer that thought that was very helpful. So it was our prize, but she gave it to me in a structural engineering firm. To try to go from the first principle here, we use rebar or steel in concrete for many reasons, okay? Let's go there first. And the general topic is going to be an initiation today of the discussion about corrosion control of metals now. Because we talked a little bit about plastic. You can always rewatch the lecture. If you think all the info was there, it was too quick, you can always ask me a question, even interrupt me. So, dollar first, okay? So cheap concrete, you know, aggregate, cement, all that stuff, even water. Water, yeah, it's getting more expensive, but, you know, still relatively affordable, easy to transport if you don't need it to be pure. It can be brittle. That's one thing. So this is really the big plus here. So this is the reason. Now, what you try to do when you can save money is make sure you still get what you need. Okay, so one thing you need is a certain form of reliability still. And that's where we have to be honest here, that the reliability for that concrete structure that has steel reinforcement is not driven by only one of the components, it is both. Okay, so the reliability is good concrete or grout or cement, depending what the application is, and then we'll say good steel. And plus, this is not a design class here. Okay, we're just really trying to talk about how we make material and why we make them that way and for what application. Good concrete, well, we don't want the concrete to let salt from the road, for example, chlorides, degrade it to the point that now you get kind of potable rainwater on that rebar. So it's very important. The concrete is a very, very important part of having a bridge, I mean, you name it, just the walkway, stay crack-free. What else we need the concrete to do? Well, it's filling space, it's good, it's built up the thickness, so you got a good bending resistance, it's a hard surface, it's wear resistant. I like that it's light colored so it doesn't get too hot. You know, when I can afford not to have a gravel driveway, I do think I want to put, you know, concrete as opposed to asphalt. But then going back to what's going on here with respect to the good concrete and the good steel. Well, the good steel, okay, you can protect it. So you can say, I'm going to epoxy coat it. So even if there is some infiltration of water and chloride and oxygen over time, it's going to have to go through the epoxy before it gets to the steel surface. So that's one way to do it. And we'll talk a little bit about coatings later. But there's not a whole lot really at our level of discussion today that is really mechanical. I could say a few things, for example, that the way you use this combination of concrete and steel is going to be very different if you're thinking about just a sidewalk than if you're thinking about those big pressure pipe. I talked about, you know, 16-foot diameter pipe that are under very, very high pressure. So you have different expectation. If it's the sidewalk, eventually this is going to fail. So it's gone. And then this will be good only for so long. So you'll crack the concrete so the bridge doesn't fall. It's awesome, like here on Memorial Drive. You still don't want it to start becoming into so many small pieces that the piece fall into cars. That's not good. You know, if you're talking about a pedestrian bridge over here on Memorial Drive, that's where you really call for a repair. But again, you made a safe enough structure for this application by saying, if I lose the integrity of my concrete, my good steel is going to give me a pretty good warning sign that I got to go and do something. So in parking garages, when you start seeing crack, they'll go and drill at those spots, and then they can put some anodes onto the rebar to protect it. Then they put a cover back, good for another 20 years. They didn't even need to stop the service for more than a couple days. So that's the reason, right? You don't want service interruption. Otherwise, probably be cheaper to just replace the floor, but it's more involved. Yes?
Just like zinc or...
Yes. So zinc anode or magnesium anode, because it's harder to diffuse into the concrete and get that galvanic effect, the sacrificial effect, because you're diffusing into a solid. So I think you'll have to check whether the most standard is, you have to put it close. So if you're in water, you can put your anode there and have your structure over there, it's still working. But here, and it's okay because you're digging it out anyway, but you have to put a lot of these things in there. Very good question.
And just a slight aside from the steel thing, are there, like, people I think have been looking at using fiberglass reinforcement for concrete or things other than steel? Has any of that?
Okay, very, very good question. So Greg asked about not using steel, using composites instead, and I think you were not here yesterday. So I no, you'll watch probably the lecture eventually, and what happened, it may not even be online yet. So I'm not blaming you, and it's a good question, I appreciate it. So I didn't kill the composites yesterday, but I reminded you that if your top objective is to save money, may or may not work, depending on what you're thinking about. It was a very good question. And I'm glad I'm using the board so I can try to stay organized here and going through the details of this. Any other questions? All right, so we were going to talk about, now that we have the big pipe. That big pipe, first of all, you're not going to put de-icing salt in it. So the likelihood that you're going to have a degradation of the inner layer of concrete is significantly reduced. And on the outside is probably where the biggest risk is, because when you put these things into the ground, if you hit that cover. So I didn't draw it, but on the composite example, there's quite a bit going on here. Let's see. On the composite example that I presented yesterday, I said you can take a cylinder and then you're gonna wind around your reinforcement. You really spiral it around, and you keep pulling on that wire while you put it on. So the pipe starts looking like this on the outside. It's got different layer of reinforcement. And again, these are going all around. So this core becomes in compression, and the tension is here in the wire, and it's very, very high. Okay. So as part of the last stage of manufacturing is you put a little bit of a cover on this, because you don't want the steel to corrode when you put the pipe into the ground. And that's, so what goes on top of these wires is what I referred to as the grout. May not always be grout, but that's what I know. So if that grout deteriorates and you start getting just even moisture, a certain level of moisture and reaction, corrosion reaction, taking on those wires, they'll break, they'll snap, because you're inducing, and it does not snap just for that reason. It is under cathodic protection, so there's essentially production of hydrogen in certain conditions, and that causes things to snap. But it's a different behavior in this case than a thickness reduction. So can you make a wire that'd be a little bit more resistant to that hydrogen? Yeah, there's a little bit of a compromise there. And that's, I guess, my example that is more specific to good steel. So if you say, you know what, this environment, it's going to go under the water, for example. So it's going to be 100% submerged. And I can afford to have more of these wires, but a lower strength. So if there is a moisture penetration, they're not going to break right away. That's an engineering decision you have to make. And I'm not going over all the factors that are going to influence that. I think what I'm going to do is finally get to more of the science, and hopefully I capture a little bit the importance of understanding here what's going on. So why is this thing losing so much thickness? And one important thing here is you can see, let's put it here. I don't know what the camera is doing, but it's not the same, right? That's a problem. You know, a chain is only as strong as its weakest link. Well, the corrosion here is not uniform, and that's very, very common. So if you want to use just a rule of thumb that's in quite a few corrosion books, is you'll say your maximum corrosion is twice the average corrosion, just as a rule of thumb. It's something that I do remember because I had to use it. That always helps when you need something. When you really need something, you find it. And then when you make a mistake, you tend to remember it too. Okay. Science. So let's get rid of all that stuff. I only have so much time left anyway. I mentioned as an introduction last lecture that the corrosion of steel always involve kind of a battery effect. So the battery effect is the anode and the cathode effect. So you've got all your stuff going on here, and there's always going to be one that's going to be essentially causing the reduction reaction and the oxidation reaction. So let's try to go through that. You can see here the surface very rough. Probably what I passed around is more useful, but for those watching online, it's a typical piece of steel that comes looking at one of the tunnels on Stowe Drive. Big project. Can't stop the traffic. Need to figure it out. Oh, that's a better drawing than what I put on the board here about having an anode and a cathode, and you can see why you're drilling a hole, right? This is not constant. Okay, so what causes this? Okay, why? Because I only talk about having one piece of steel. Why the hell am I thinking about having an anode and a cathode? And again, it is thermal activation. So at some point in time, there's going to be more electron here and more proton there, more ions there, and you start having that effect. Now, that effect propagates because that's a reduction in the overall thermodynamic energy. The system wants to corrode, and any fluctuation is going to start that process, essentially. Does that make sense? Yes.
So how does the hydrogen come? So where does the hydrogen come?
Very good. So the question is where the hydrogen come, and it's from the water. Because water, H2O, will always have an equilibrium with a certain fraction of O2 gas, and then, no, not necessarily. It depends on the environment. So you could say it's 2H plus O minus 2. That's a possibility, okay? In this case, you do not have the hydrogen, but then you have other reaction because you do have some oxygen in any environment, and it's not in the form of O2. So if you try to make another equation like this, and you're allowed to do that, right? Because here we have too many variables, so we can't solve the problem. So let's say we're adding oxygen. Okay, so that's an oxygen gas now. So what am I going to do if I have oxygen gas trying to make an equilibrium with still the HO2? So that's another equation. So let's say I try to do that. I'm just going to draw a line here. So can you help me here? Can you help me make that equation? plus what? Because I can't have an ion there because there's no ion here. There's no ionic state there. So what will make that an equation that's valid from chemistry? Hydrogen. Thank you. Thank you very much. So if Professor Eager says he's got something against doing derivations in class, well, I guess I decided to take exception this morning, making a special. And I'll mention to him about that. So he comes very prepared again, which he's really good at. So thank you. It seemed like you guys engaged. I appreciate. And now, how much oxygen there is going to affect how much hydrogen, right? Because there's a little bit of an equilibrium constant here to think about, stuff like that. So it's never easy, right? But there's always more complexity into this. But at least now you get a little bit of a sense. And it was a very good question. I appreciate it. So, I mean, to some extent, this is now becoming a little boring, right? Because we've established we're going to have ions there. We've established together that there's going to be an anode and a cathode just by random fluctuation into the system, and the presence of oxygen. The presence of oxygen is the driver because a piece of metal, a piece of iron that is oxidized is less energy than a piece of iron that is not oxidized, and that's your driver. And what the water and the oxygen does, it enables that driving force to materialize. Very good. And that's what happens. It forms a big rust layer. So what you're looking at on the screen is a piece that I collected from the Storage Drive tunnel 5 years ago, and that tunnel's still there. So should we stop traffic? What do you think? Anybody? Should we stop traffic? You guys seem to have a little confidence in me thinking that if I thought we should stop traffic, I would have said so already, right? Yes, I'm a professional engineer. So the reason that I got scared at first and almost called 911 is this is almost the thickness of that steel beam that was out there, 3/8 of an inch. So I almost called 911. But thankfully, I recall what Professor Eager said in some of the lectures that I listened to a long time ago, that the oxide is not as dense as the metal. So in simple terms, let's say the steel density is 8 grams per cubic centimeter or so. I think those are the units. Then here you're looking at about 1/3 of that, so maybe 1/4. So when you take a piece of steel, let's say this thick, and then it corrodes, it leaves behind a corrosion product, let's say this thick. So, because I had some knowledge of that, because I was listening in class just like you guys are, I did not call 911, and therefore I looked good when I came to the office because I got my boss scared, and then I told him that it was okay. So it gave me a lot of credibility as a young engineer, which is very important. We only have 5 minutes left. Any questions? Do you want to continue or you want to ask questions? Because we go all day, but it's interesting, huh? Corrosion, I think, is interesting. It wasn't interesting to me the way it was taught to me, and I'm not blaming any. Maybe I was not paying attention. Maybe they didn't know about it in a practical sense that I've had to build since I graduated. So I want to be clear on that I did not know what I just tried to teach you when I graduated from a good school. So that tank here, it's got holes in it. Can you explain it? Yes, no, maybe? Let's go back to this. What happens is the reason that you cause this little divot into the surface, that happens again all the time. You cannot have what we call the uniform corrosion. And I have a video on this. Maybe I'll post it. Maybe I'll show it next time to get people excited and hopefully maybe get some more momentum on this topic for the next lecture. So let's say you got a piece of coal tar, a little product that you use to protect the steel, but that coal tar at the same time, when you start having a reaction, you don't have the same oxygen inside of it and outside of it, and that's permanent. To the extent that piece stays right where it is, it's going to keep acting at the same location, and you could call it pitting, but we want to be very careful with pitting. We're going to cover pitting later. It's a little different. It involves a protective oxide layer. So I'm sorry if I can't go faster. You're gonna have to walk through me on this. So this piece of metal, yeah, it was probably had a coating on it at some point. It was put into the ground 60 years ago. I mean, there's no way it should still have been there, but it was there, right? And that's the reason I had to go and look at it. One reason why it stayed in the ground so long is it was in clay, and therefore the clay contained the gasoline to some extent. So the homeowner, was filling it in and still having some left to use through the years. So I didn't realize it right away, and that's a problem that is now fixed if you have a double wall, if you have a good cathodic protection system, things like that. But this, to some extent, let's be honest, it's relatively bad because overall the tank's still there. If you take the weight of that big tank, it's still pretty good, but it's got holes in it. And hopefully now you have a little intuition as to why that happened. The corrosion localized. And therefore, it's not just a factor of 2 between the maximum corrosion thickness and the average, it's more. It's because the soy in general is 30. So it's not going to be consistent from one spot to the other, and therefore you're more at risk for this type of effect.
Well, and I would presume just like the concrete, if you're trying to cathodically or with anodes protect it, as opposed to having something in seawater where the circuit connects really well, you have spotty connection from location to location on the tank.
Yeah. Hey, if anybody, Professor Yeager distribute money here, so if anybody wants to have a microphone for the people asking questions, they get some form of a reward here, because what Greg said was a very, very good question. He said, hey, what you said about the concrete and having to have a lot of anodes because of the difficulty to homogenize the iron content in the concrete does apply to here with the clay. So if you have clay and there's a little bit of organic soy in it, all of a sudden you have a different chemistry, and it's very hard for your remote anode to take care of all of that. Having said that, if your system is really working, it's got a strong enough current, then you're in good shape. I mean, over here, the anodes, I don't know if they had one. I haven't seen it. So it's a small variable there. So it is possible to keep a piece of steel not shiny, but free of section loss if it remains cathodically protected. Now, of course, by asking a good question, you have me jump the gun here, because if you're going to do cathodic protection, most of the time you do put a coating on anyway, so you minimize the amount of current that you need. So that's very important as well. And I won't even look what the next slide is. I really appreciate you guys' participation. I hope that the lecture was useful for those listening online. Thank you very much.